Good afternoon, everyone. Had a good lunch? Yes? Did you enjoy Lugano today with the wonderful weather? Yes. It's not too, actually, is it still good? Okay, fine, I can't tell. It was good when I checked earlier on. So today I'm going to speak about what's sort of ahead and what is currently possible today with everything that you want to do on the web that is not just flat. All right? We love non-flat stuff. There has been a wave of parallax scrolling things that have horrible performance on mobile and make people sick. This is not about that. This is about where 3D on the web makes sense and how you can get started with it today. So quickly, who the hell am I? I'm a very, very serious programmer that happens to sometimes speak in onesies. You might have seen or met me last, no, actually that was in March or something, or February, whenever that thing in Zurich was, because I was that in Zurich at Vox Days. I'm from Zurich, ta-da, and I work in a company called Archaeologic, where we do a lot of WebGL things, because our product is focused on 3D on the web and interactive. That's tricky, but we got it working on mobile phones and everything, and so I'm going to sort of share how that works with you today. You also find me on Twitter, slightly cut off, Geekonaut. That's going to be fine. Slides will be online, but if you feel like tweeting or sharing anything from the slides, have fun taking photos. Right, so first we're going to talk about what this WebGL and spatial web and stuff is and what you can do with it. Once we figured out what it's good for, we're going to figure out how to actually make it happen. Once we have figured out how to make it happen, I'm going to tell you how you can actually do the same things, basically starting today, hopefully. And then we're going to see where we are kind of going and where the fun stuff is that we are still figuring out as a whole community. So what can you do with it? Well, first of all, shameless plug, you can do full-blown 3D applications on the web. So this is an application that runs in your browser and lets you exchange the furniture and lets you create these 3D tours and everything. And it's really cool and really nice and really fun. So you can actually build software that does things entirely in 3D or WebGL. WebGL is also really powerful for 2D effects. We're going to see why in a bit. So if you want to implement Photoshop in the browser, that is totally possible without Flash, Silverlight, or Java, just using WebGL. But not only that, you can also use it where you don't really sort of expect it. For instance, this is an article from 2 years ago, from New York Times, where a bunch of people climbed up a mountain. And if you're on a small screen or on a device with very, very low internet speed where the download of this 3D stuff takes too long, you just get a normal news article. You get text, you get images, you could theoretically get videos and all of that. Here there's no video as far as I'm aware. And it just scrolls and it's just normal article really. However, if you have enough screen estate and it makes sense to display more information, you get this enriched experience, right? You can see how actually hard it must have been to get up this mountain, and you get a better feeling for how high this mountain has, or still is, hopefully. And this is a volcano and blew up or something, and I don't think that is the case. Because, you know, these images, let's wait for it until it comes back. These images are nice and fine, but they give you very, very small insights into what actually happened and what the spatial relation is. So you're like, yeah, there's a bunch of people having champagne, apparently on a mountain. For Swiss people, that's not a big thing. But if you look at that particular mountain, that's not the easiest climb. That's not a hike. That's a proper climbing, right? So it gives you more information on how sort of space actually relates to the story. And this is progressively enhanced because you still get the normal story if your device does not support WebGL. You can also do crazy stuff. So I wouldn't say all the infographics that we do make sense in 3D, but if you have a bunch of quadrocopters that you basically take up onto the summit of Matterhorn and then actually have them fly with laser scanners around the mountain and scan the entire mountain, this is probably the best way to visualize this data set. So this is actually like 20-something million data points, and with some performance tricks and tips, they actually made it work nicely and progressively. As you can see, it reloads more points as you zoom in, and it sort of thrashes them out once you zoom out again. So you get a pretty good idea of what the data set actually represents, which makes sense for space in data. You can use it for all sorts of weird things like this. So basically you can take photospheres, which is basically a panoramic shot, but you also do up and down, so you get a full sphere around you. And you can use that to show people how awesome your hotel is, how ancient Rome looked like, and all that. And you can obviously also create virtual environments, so you can put your students into spaces that they can't go for whatever reason, for instance, because they don't exist anymore. So this is pretty cool. This is Mallorca, by the way, and I was bored and I got annoyed with all the tourists. So I'm like, I'm going to check this out later on as well. Yeah, and there's much, much more coming. So as I said, you can do 2D applications. Behind this link, as I said, the slides will be online. Behind this link is an implementation of Pac-Man entirely on the GPU, which is absolutely crazy, but it's super cool that it works. You can do CAD, so Autodesk, watch out. Obviously, you can't do really, really complicated things like things that actually take a lot of computations, where you have parametric objects, might require a little brain power from you to save brain power on mobile GPUs, but it can be done. I'm not saying that you can do a full-blown CAD application, but theoretically you can if you just put a lot of effort into it. If you have product configurators, so for instance, if you sell cars or if you sell customizable furniture or something like that, there's a psychological effect that if people customize the thing, they basically have bought it already. So you can do that in the browser. They don't have to install any application. They don't have to run any plugins. It's just they go to your shop website, go, ooh, yeah, I'm going to try night blue. And, ooh, this looks awesome. And I'm going to put a spoiler on it. Oh, yeah, that looks great. And some decals and some flames and stuff. And they're like, ooh, I'm going to take that car if they are 16. Anyway. So yeah, that works pretty well. Product showcases, if you have a product that is quite large and has to fit in other things, again, furniture, for instance, or if you have very high-end, I don't know, if you have a high-end phone, you might want to show that off so that people can actually see how the light reflects on it and all that jazz. You can do that interactively. Also, again, without Flash and any of that, you can just do it with WebGL and JavaScript, and you have a plugin-free experience. And last but not least, games. So Unity, for instance, now actually allows you to directly export into WebGL. So you get basically just a website with a loading bar that loads for a couple of minutes, and then you get the actual game. But a lot of JavaScript game libraries, for instance, Phaser and Pixie and all these, use WebGL whenever they can, because even 2D operations are much, much faster than just on the canvas. And you can do that on the browser, and it's responsive and everything, and it's super nice. Cool. So speaking of the web, we have a bunch of different graphics APIs. I'm leaving some out for very well reasons, but let's actually explore what APIs do we have to actually influence how things look on the web. Well, the simplest one is the DOM. What? The DOM how is the DOM visual? Well, if you think about it, all I specify is I want a label that says email, and I want an input field, and then I get that. That is visual, in my opinion. However, it has a few problems. It has a few advantages as well. The advantage is it's declarative, so the browser can actually figure out how to do that best depending on the device I'm on. On a mobile phone, it might look differently than it does on a full-blown desktop or large screen. Just imagine a date picker or time picker. If I basically say this input is a date picker, then it might look very different on the desktop, where it gives a pop-up that just takes a little more space on screen, whereas on mobile it might actually switch to the native date picker at some day. Hopefully, we're still not there yet. So it makes actually best use of the device that you're on, which is great. This declarative powers that basically shift a lot of responsibility to the browser have some downsides. It's pretty abstract, right? I haven't really said like, oh yeah, I want this, I don't know, 500 pixels long and I want this to be green or whatever. I basically abstractly say I want an input, and then the browser figures out what that means. That's cool, but it also gives me only limited options. I can only do so much with this, what the browser gives me, right? The cool thing is this is aimed at structure and content. That means it's by definition easily accessible. So screen readers and everyone who has visual problems gets a very nice tailored to the particular way of viewing it solution without me having to do that. So don't just swap out your DOM entirely for something else, because this actually makes sense. And then we came up with CSS. And CSS allows us to be a little more specific on how things look. So here I have a div, and I give it a class of box, and I say, hey, I want this box to be 150 pixels by 150 pixels, so that gives me the dimensions of how large this box will be, and I want its background to be red. Okay, That's nice. So I can now actually make things look different than the browser's defaults. So that is wonderful. However, it is still declarative, so it's still abstract. It's still a thing where I tell, hey, this is the end result, right? This is the end result. I want a box of these dimensions, and I want it to be red. That's it. I still do not have access to particular 1 pixel by 1 pixel. So if I would have a 500 by 500 pixel screen that I want to manipulate each of the pixels, I would have to get 500 by 500 times a div that I can style like that. That is pretty bad. So that's a bit annoying. I still do not have access to pixel level graphics. Again, it's implicit, so there's a lot in the CSS specifications that goes into how CSS is actually turned into graphics. So I still do not know exactly when and how things will be drawn, and especially there's this thing called, who here has heard of layout thrashing? So layout thrashing, what happens is when you use JavaScript to change the layout in CSS, make this thing green. It doesn't happen right away, because the browser goes, maybe someone is actually doing some other changes as well, so I'm going to wait for just a few milliseconds until I actually do this thing. And then it basically batches it up. So if you say like, hey, make this green, then make it 500 pixels, then make it, I don't know, give it a border of 50 pixels, make that border green as well, and then do this and then do that. Basically, the browser waits a few milliseconds until it actually does all these things in one go. Because if you change the size of the box, or anything really that affects how content flows around it or inside it, that means it has to recalculate how the site basically is laid out. And that's expensive. So it basically tries to avoid doing that a lot of times. But what happens when you do change that thing to 500 pixels, then tell me how large it is, then actually put a border on it of 5 pixels, tell me how large it is now entirely, and then make the border green. Now tell me the color of the border that I just gave you. Then basically, whenever I start asking for it, it makes sure that it does not have pending changes. So now, after each of these steps, it actually did a relayout, and that is expensive because it has to recalculate how the page basically looks. So that means that actually can cost you a lot of performance. That makes your site slow and horrible. So what I'm trying to say with this is the DOM is pretty clever in how it does your changes. The problem is you have no access to this cleverness. You can't say, please don't be clever. So that's a problem, potentially, especially if we do games and we want to be the clever ones, not the DOM shall be clever. So we have Flash to solve that problem. Nah, just kidding. We have a thing called the canvas. Yeah, don't go for Flash. Just don't. So we have a thing called canvas. Canvas is nice as it is supported in most browsers. Hurrah! And the canvas finally gives us pixel-based access. So this is how it looks when I want to, by the way, this is green because I'm showing where it's actually repainting. So the browser is constantly repainting the entire canvas, all right? Even though only this little red thingy actually moves. But here's how you get it. You get your canvas element, nice. You get a 2D context. So basically you now get access to the pixels that are in the canvas, nice. You say, please fill with red. And then you ask the browser, whenever you paint a frame, or the next frame you paint, and every frame after this, please call my draw function. And my draw function clears out the entire canvas. By default, that makes it like black. Then please fill a rectangular starting from position X, and then 10 pixels from the top, and then make it 50 by 50. And then I just, on each of these iterations, so this is basically a loop, so that we call this function, then we do stuff, then whenever it's ready for the next frame, we call the function again, whenever it's ready for the next frame, we call the function again, and so on and so forth. This is our render loop. We basically just increase the position of our rectangle, and when it's actually reaching the right-hand side, we reset it back, and then it just does this wonderful motion. But as you can see, it still paints the entire rectangle. Why is it not clever? Because the cleverness is now with us. So this is cool. It gives us an imperative access on a pixel level. So we can now program what we'll see, and we get fine-grained access because we know that our drawing function will be called whenever the browser is ready for a new frame. So there's no thing as, oh yeah, no, we cache it this time and only do it next time. No. Whenever the browser is ready for the next frame, we're going to get our function called. Problem is, if our function is too slow, we actually get a drop in frame rate. Bad. It gives you some kind of hardware acceleration. That means yes, you're now painting on the straight onto the graphics memory, and it's in a separate layer. That's what they call it in browsers. So basically, it's not part of the entire layout flow of the thing that you have there. Is this entire rectangle that is your canvas is isolated from everything else. That's nice. But you don't really get full hardware acceleration, and we'll see what that means in a bit. But it gives you dependable behavior. There's no cleverness involved anymore. The problem, as I started to say, is we have limited hardware acceleration. What does that mean? Scaling an image, for instance, actually takes a lot of effort on the GPU. No, sorry, on the CPU, but not on the GPU. But if we were to basically scale our own things, images are fine, kind of. But if you say we have these 2 points that we want to draw a line between, and we want to scale that up, that means that you are having to actually get the line redrawn using the CPU and not the GPU. The GPU is really, really good at scaling, but we are not using any of that power. GPUs also have these cores called shader cores or shader units where you can execute functions that are really, really fast because they basically run in parallel. We're not having access to that either yet, all right? So you get a lot of tips and tricks on how to optimize performance. And one classical one is the layered canvas. So if you have a game and you have a background, and then you have, I don't know, enemies that move and your player that moves, and the background stays the same, then they say, well, you know, layer them so that you have one canvas for the enemies, one canvas for your player, which might not move as much as the enemies because they are constantly moving, and then have another canvas below that that actually renders the background because the background change is even less frequent and all that crap. They also say, hey, if you sort of do lines and stuff, try to combine them into one big cause. So basically you have paths. You say like, draw this line, then draw this line, then draw this line, then draw this line. You can basically put that together by saying from here to here, from there to there, from there to there, and there to there is one draw call. And draw calls is when basically the CPU throws it over to the GPU to actually render it. So if you make this transition a lot, that is expensive. If you do it less frequent, it's better. Yeah, and then obviously, I could not just clear the entire canvas. I can only clear the parts that I know have changed. But in real applications, that is quite hard. In my wonderful application here, that's easy. I just clear out this bit that basically, this moves by 1 pixel. So I just clear out the bit in front of or behind it so that it doesn't keep being read. But in a real world game, that is actually quite hard to do. And there's a bunch of pitfalls like rendering text, scaling text, rotating images. All that has performance implications that are quite heavy. Another thing is it's imperative, which is cool. But that means if you're drawing pixels with JavaScript, you are on the main thread. So now imagine you are, for whatever reason, think, hey, it's a good idea to draw pixel by pixel this image onto a full HD frame. That's 2-point-something million frames. So you have 2-point-something million operations in JavaScript. And you know how much time you have? Not much per frame. So it's probably not the best idea. And then comes along WebGL. Yay! So how does that help us? First of all, it helps us in majorly every browser that is recent and evergreen. So sorry, IE 9, 10, and 8, and all these, they are not evergreen. So 11 gets you covered. All Edge browsers have it, and it's pretty okay. And it actually works well on mobile as well. So this is the smallest example I could come up with to get started with WebGL. Don't try to read this, right? But this is the amount of stuff that you have to get moving to actually start working with WebGL. And all this beauty gives you that. That's a lot of code for a white triangle, isn't it? So yeah, this is a bit of a problem. And a lot of people that want to start with WebGL come to me and say, I would really love to play with WebGL, but I have this problem of WTF. And I'm like, I understand that very well. I've been there myself, my good friend, but trust me, it is worthwhile going for it. So the first problem is, as depicted here, it is a very, very verbose API. So this is the bit of HTML that we need. This is some weird-looking code. Then we just do random shit with a GL object, and then we compile shader, what the hell, and then weird attribute pointer, what? So let's actually go into what the hell all this means. So you have a lot of moving targets at first, but they're not that bad. I'm gonna walk you through. Don't you worry, stay calm, don't panic, it's gonna be fine. Because you get a lot of cool benefits. So if you actually move through these moving targets at first, what you get is you get the full entire pipeline, what happens on the GPU, you get to influence that. And that means you're basically moving most of the work off your main thread into what's happening on the GPU. And the GPU is really, really good at doing graphics because this is pretty much what their job, right? And the biggest difference is it gives you parallel pixel access. So if we remember doing the canvas stuff, I would have basically a for loop that draws pixels onto the canvas, which is bad because a for loop in a single threaded thing means everything happens after each other, right? That's stupid because we have an image, for instance, and this image pixel, the pixel number 5, does not depend on any other pixel. The pixel number 5 is red no matter what happened before or after it, right? So theoretically, we could be able to just do it in parallel, but we can't because JavaScript. So here we now finally get parallel pixel access. And we get to write programs that run on the GPU. Hell yes, Bitcoin mining, here we come. No, actually Bitcoin mining is blacklisted, I heard. I haven't tried that. So yeah, just a quick overview. So a full HD frame has 2.03 million pixels. If you think of 24-bit colors, that excludes alpha in this case. You have a whopping 5.3 megabytes, far too much for my floppy disk. And you want to have 60 frames per second because that means that your application is smooth like silk. But that means you have efficiently like 10 milliseconds. Theoretically, it's 16.6 milliseconds for each frame. However, the browser does have to do some stuff as well, like event handling and all that. So effectively, you get 10 milliseconds. So again, JavaScript running a for loop, running 2 million times in 10 milliseconds. Good luck with that. So basically, that's your CPU when you do that. And as it's specialized, that's your GPU. And we want to get there. We don't want to sort of overwhelm our poor CPU. We want to get our GPU going with what it's best at. So I've been talking about a few terms already. I've said something like shader, and I said something like attribute, pointer, and vertex and stuff. And what the hell is a GPU anyways? So basically what the GPU pipeline allows us is to run a program that takes a value, transforms it, and outputs a new value. That's a function call, isn't it? And the cool thing is, as we just have a value that has no dependencies, as I said, the pixel number 5 is red no matter what. We can transform that. For instance, we could invert colors and make it, I don't know, blue. And then get the pixel value blue out of it. And we can do that in parallel. There's no dependencies, there's no concurrency. So we can say, hey, here's these 5,000 million pixels that I need to render. And then the GPU goes, yeah, sure, I have, I don't know, 1,000 render cores. So just, 1,000 pixels go through at each iteration. So that is really fast. Also, this entire processing is highly specialized. So it doesn't have to deal with things like task switching. The GPU doesn't care what task actually gives it the data. As long as the data comes in, it's going to transform it, it's going to put it out. It's none of its business. So it's really, really optimized for vector math, for floating point math, and for I/O. Most of the things are actually accelerable in hardware, so it has specific units to do scaling operations, to do vector operations. It's highly specialized hardware. And basically, if we program it, all we have to specify is what the hell is f, right? And maybe what kind of x do I want. But the graphics card will take care of getting the y onto screen. Cool. So with that, let's have a look at the pipeline. First of all, we need to define the points we want to draw. Now, we're not going to draw points, but we're going to actually draw points that happen to be connected to other points. Because if you think about it, we want to draw shapes most of the time. So how do we draw shapes? Well, the easiest thing to do is draw a triangle, because with a triangle, you can basically approximate every other shape, right? A square is just 2 triangles. Nice. A circle is just a lot of triangles put together with the same center. If you put more triangles, it looks more round, so that's pretty much all the trick. So pretty much every shape that you want to draw can be approximated by triangles. And in a triangle, each point is connected to 2 other points. And this has a definition because we like to invent new words. So we don't call it a point, we call it a vertex. And because English is a fun language, it's going to be vertices if it's more than 1. So we put these into, basically we put the positions of our vertices into an array. And because we want to be fast and efficient, we're going to say, you know what, we're going to take a float because, you know, then we have very fine-grained positioning control. So we're just going to take floats with 32 bits and just put them into one array. And then we have this in an array. Cool. But what do we do with this array? Well, we want to pass that into the graphics card. We want to tell, like, here's a bunch of points. Go, GPU, do stuff for me. And we do that by creating what's called a buffer. So this is OpenGL terminology, and in OpenGL terminology, a buffer is basically nothing else than a bunch of memory. So this is just a piece of space where we can basically pour all our points in, all our vertices. So now we have this array, and we put this array onto the GPU by creating a buffer. Okay. Now we have it in memory on the GPU, but how do we sort of, you know, get pixels from that? Well, the third step is we run it through a vertex shader. What? So again, we have a bunch of vertices, right? Points that we want to draw. We have point number 1, point number 2, point number 3, and that forms a triangle. That is cool. All right. Better? All right. Sorry. So we have our points that we want to draw. We have our vertices that we want to draw. But we probably want to do things where we don't want to have to re-upload the entire points if something changes. Just imagine, I have this point here in memory. And it should stay there because actually uploading it back to the GPU takes a little effort and actually is expensive. So I have this point here, and then I have my camera looking at it so that it's straight in the middle of my camera. But now I rotate my camera. Now this point has to disappear, right? So as I'm turning it like that, the point has to go like this, and basically, actually in memory it stays at this position, but on the screen it moves. How do I do that without having to use JavaScript to sort of move the point around? Because if I move the point around in JavaScript, why am I doing all this, right? Then I can just use Canvas 2D. Here's where the vertex shader comes in. The vertex shader is a program on the GPU that can run independently for each of our vertices. So that means our 3 points actually are run at the same time. So it doesn't have to transform these points one by one as we would do in JavaScript. With 3 points, that's not a big difference, but imagine 5 million points or 5,000 points or 50 points. There you actually see the improvement. Now you run this in one go and instead of after one another. So what this vertex shader does, it gets another value from JavaScript. It's just one value that says where is the camera looking, right? So where is the camera facing? And then I just change this one value in JavaScript, for instance, or somewhere else. I change this value, and that actually tells the shader to produce a different value as its output. So it takes this point that never moves and takes this information where the camera looks and then shifts around things. Another example would be, and that's where 2D stuff comes in, you have a very complicated circle shape with 5,000 points for whatever reason, which is ridiculous, but let's go for it. You have 5,000 points, and you want to scale the circle up. How would you do that in JavaScript? You have a loop that runs 5,000 times, one after the other, to basically move the points around so that the circle appears bigger. Here you can have basically the same function run as a vertex shader, where it takes these 5,000 points in one go, and basically shifts them around without actually changing the memory. In memory, they are still the same circle, but now we say, hey, vertex shader, please scale this by 2. And then it actually scales it by 2 by moving the points around. So we have a parallel access to get ad hoc, without changing the real memory, new positions where we want to draw on the screen. Nice. So now we know where we want to draw on screen, but we don't know what we want to draw on these positions, right? So what happens next is what's called a fragment shader. That's another function that runs on the GPU, as the name shader kinda implies. And what it gets is a position that it has to color in, and some other information that we specify. So we can say, hey, by the way, put also in whatever, a number that keeps increasing over time, for instance, like milliseconds since 1970. And then it actually calculates the color from that it wants to put out. So here we can say, hey, for instance, if I pass in a value of blue, then please just make it blue on every position. So this is a function that actually allows us to color in all the pixels in between. Right? We have our triangle, and now this function runs in parallel for all the pixels in between. That is nice. So once this has done its work, we can actually put out pixels and have some nice graphics and be ready with it. And it's very sparkly and very cool because these two run massively parallel. So that means we don't have to wait for one pixel or one vertex to process, which is nice. Cool. But that's a lot of stuff, right? There's like 4 steps to actually get stuff on screen. But fair enough. It's not too bad, actually. Quick vocabulary session. We have defined this one already. So these are our vertices. A little more visual here. And we want to connect them. And there's one more word here to learn, which is face. Basically, a face is the triangle that we want to span between 3 points. 3 vertices. So here you see each of these vertices has at least 2 connections. That's why it's called a vertex and not a point. Mathematicians. We might want to put an image onto it. So this would be an input for our vertex shader. So this thing goes into our vertex shader, and it knows, aha, in between I have to draw pixels from this image, and it does that in parallel. So it doesn't go like pixel 1, pixel 2, pixel 3. No, it goes like this pixel, this, and then here, and so on and so far until it's actually ready. Cool. There's also something called the rasterization. So here's the thing. Our pixels, unfortunately, are not mathematically correct. Because we have these floating point numbers, so we might have very, very small in-between values. So for instance, here's one vertex, here's another vertex that goes over a bunch of pixels, but it's not perfectly just pixel. Each pixel isn't perfectly where the line should be. So the GPU automatically for us figures out, you know, this is not as much in the triangle as this pixel is, and this pixel is even less in the triangle than the other pixel. So I'm going to call the vertex shader for each of these slightly colored pixels, but actually just multiply the value that the pixel shader says should be the color with how much inside the shape it is. And that gives you a fragment, so each of the non-white pixels here is actually called with a fragment shader and has to be colored in. There's also this concept of a normal, which is kind of useful for lighting. So just imagine, so this is our thing that we're going to draw on. So this is a plane that faces in this direction. It faces towards you, right? The beamer or the projector actually throws light at me in the opposite direction. So we have two vectors. Basically, each of these directions are called a vector. And they meet each other, and they have a 180 degrees angle between them, which means the light is full on. But what happens if I take this plane and move it by 90 degrees so that it faces that way? So the light still, oh Jesus, is that me, actually, this sound? Ah, Jesus Christ. No, it's fine, I can live without my glasses. Where am I? All right, where was I? Oh yeah, so now it faces this way. The light comes from here, so we have a 90-degree angle between the two vectors, and that means the light is not affected at all, right? Because the light goes this way, so it basically just passes my surface. I know I'm not very flat, but just trust me, if I would be flat, the light would not affect me. I'm not very thin thanks to Swiss chocolate. And lack of exercise, really. So these normal vectors basically just represent where is a face looking at, so that you can use the light direction to figure out how much lighting is actually applied. You can see that here. This one is much more affected by the light that comes in than this face back here, which makes sense, which is how it works in real life as well. Right, that's just terms that you should have heard. We have covered shaders. Shaders are programs that run on the GPU, which is nice. They are written in a different programming language because JavaScript turns out to be not very optimized for running on GPUs. So yeah, GLSL or GL slang is the language that you're going to write, which is a typed language, looks a bit like C, but less frightening for many people. It has a lot of accommodations, like it has a lot of vector functions and all that, so you don't have to worry that much. Again, the vertex shader takes a point and gives you a new point by scaling, rotating, or just moving it around. The fragment shader takes a position inside our shapes, inside our faces, and gives out a color and a depth value that you only need when you really do 3D. So basically it tells you how far away is this particular point so that you can draw things in the right order. That's just it. Okay, with all that set aside, the good news is you don't have to worry too much about 95% of that. If you just want to get started, it's very handy if you know these terms because it's going to help you later on, especially in Googling and Stack Overflowing. But basically, you can ignore 90% of that and just go for a framework that helps you a little. I've made this thing that basically sets you up to start right away without having to worry about any of that. So what this here is a 3JS playground. So this loads a library called 3JS and does all the setup work. The setup is actually not too complicated. You basically need a few things. You need one thing is a stage, a scene, where you want to do things on. It's basically an empty space, if you wish. You need objects that you want to put onto the scene. You need a camera that you want to sort of look through onto the scene. And you need a renderer, because 3JS supports different ways of rendering. One is the Canvas 2D, which is, I think, now not supported anymore, but it was started as, like, the library started in 2010, I think. And back then, there was no reliable WebGL. WebGL was certified or standardized in 2011. So they used Canvas to sort of simulate GPU access with all the performance problems. And now they have a WebGL renderer, which renders in WebGL, and this is just all nice and fine. So you have a renderer, a camera, a scene, and something that you want to put on the scene. This already creates us a camera and a scene and a renderer and renders things continuously. So I don't have to do the setup anymore. And then you can just start to create stuff. For instance, I can say I want to, let's just call it a thing. And 3JS has this concept of a mesh. Now, what the hell is a mesh? Well, first of all, we need points and how they sort of make a shape. And this is called, in 3JS terminology, a geometry. And I'm going to go for a box geometry. And the box geometry just takes how large it is. And I just say, like, OK, this shall be reasonably large. But how is this box going to look like? So it needs a material to tell it, how is it looking? Like, what color? And is it transparent? And is it a material or is it not a material? I'm going to start with a mesh basic material. What does basic mean? What does mesh mean? Well, mesh is kind of obvious. This is a material that specifically is for meshes of all sorts. Nice. There's also point clouds in that. Basic means it ignores light entirely. So we give it a color, and it's just going to render the color and doesn't give a shit about light, which is fine. Now I have my thing. Now I need to put it onto scene. So there's a variable, an implicit variable called scene that just happens to be around, because this is a playground and you don't want to care about that too much. Now I'm just going to put it onto the scene, and then I can hit run. And this is not a box. This is a rectangle. Don't lie to me. So this function here is called on each of the frames. So this runs with hopefully 60 frames per second. So I can say I want my thing, and the thing has a rotation. So this basically gives you how much it is rotated around each axis. So you have the x-axis, the y-axis, and the z-axis. And if I want to make it spin like this, I rotate around the y-axis. All right. This is an absolute value, so we want to increase it over time. So what we're going to do is we're going to say our rotation y shall increase, and it uses radians. It doesn't use degrees, so that means 2 pi, so like 6 point something, is actually basically a full rotation. So I'm saying, okay, we run with 60 frames per second, and 2 pi is already a full rotation, so I'm just gonna, I don't know, take a value and divide it by this, and then we shall be good. And voila, we have a spinning cube. Now, we can make this a little more 90s and specify properties for our material and can say, I don't know, we want this to be green, and we want this to be wireframe. Wireframe means it doesn't color in everything, it just colors in the lines for the faces, and then we have this. Hurrah! This is not all we can do better. We can, for instance, use, and I'm not going to use any parameters because I can never remember these. This is the least useful geometry. It's a torus knot, and it looks like this. But it's quite cool, I figured. So yeah, you can do random stuff like this. And it doesn't take you that long to actually get this working, and there's a bunch of plugins that are really, really handy. So I'm going to remove this and put it back to a box geometry, and we're going to use a normal white and boring material. And there's this plugin called a webcam texture. And I can use this, and I can say, hey, the texture is called map. Don't get me started on reasoning behind that. And on each of the frames, I'm going to update the texture. Oops. And if I did everything correctly, yes, it asks me for my camera and then doesn't get access to it. Nice. Really? Oh, damn it. Damn my eyes. There we go. And then I'm trapped. Help me. So yeah. I can also map that onto the torus. Not that it makes any sense, but hey, this is a demo, so why would it make sense? Torus, not geometry, removing all the parameters, and it's going to look like, what is this? What is he doing? But it looks fun. So yeah, get started, get playing. It's fun. It's a lot of fun. And it's pretty ridiculous too. So yeah, that's that. But Jesus, why is it not doing anything good? Better. So yeah, this is fun. Try out 3JS. It's a brilliant library. It has all the things you need. Besides that, done taking pictures? Yeah, now. So that's all the things we can do now, and we can do now in production, and it's all fine, and it's all safe. But what's next? What's coming up? Well, there's this thing called WebGL 2.0, which is going to be brilliant. It's going to upgrade us from the underlying OpenGL version 2.0 to 3.0, gives us more functionality in the shaders, gives us more power, gives us more control over the drawing state, so we get more access, even more access to the graphics pipeline, and has a lot of performance improvements, such as hardware instancing, where you, instead of uploading, say you want to render a forest and you have a single tree that you want to render 5,000 times, you would have to right now upload it 5,000 times and then position it differently. There's an extension in WebGL 1.0 called AES angled instances or something, angled hardware angled instanced arrays, that's how it's called. It's an extension that basically allows you to have one time your stuff in the buffer, like you say, this is the points that make up this tree. And by the way, this is where I want it drawn, and then you just give it positions, and the graphics card basically just copies it, instead of having to actually read memory over and over again, which makes it much, much faster. A bunch of different texture formats are supported, and a bunch of other interesting things. Read up on that one. Then there's WebVR, which is super cool. So that allows you to use your WebGL experiences and applications to do virtual reality rendering. And this is where it gets interesting, because people experience things very, very differently when they're in virtual reality. So I have a relative who has a severe case of social anxiety, and he can't go places, right? I go all over the place, and I love to experience new places, but I can't really share with him except for videos and photos maybe, but that means he's sitting in front of a very small canvas where things happen. With WebVR, I can give him a headset, a cheap one called Google Cardboard, for instance, and he can actually sort of see and look around and actually experience it in a different way. It's not the same as reality, but it's pretty damn good, especially when you can't experience real things yourself. The specification is still work in progress, so we're going to see how that goes, but it actually starts to stabilize a bit. There's implementations in Firefox and Chrome, and you can do things like this. So this is using the Oculus Rift, where someone is just looking around in a place where he can't go, as this place does not exist in reality yet. Then we have this. So this is a Google Tango we have in the office, and this is actually our office in the background, which is in an old building, and it's super cool. We have a bathroom, like a proper with a bathtub and all that. This is ridiculous. You will just walk into give an office tour, like, hey, yeah, and this is our bathtub, and they'll be like, wait, what? What's that? What? You have a bathtub? Like, yeah, we use it to water cool our servers. So yeah, what you can see here is this uses the laser sensor of the Tango. And as I move around in real world, I actually move around in the application that runs on the Tango, which is quite interesting and allows for augmented reality as well. If you might go like, yeah, this is an experimental tablet thing. There's going to be a phone this summer from Lenovo. I didn't even know they make phones, but okay. There's a phone from Lenovo using that technology to actually give you a sense of where you are in space, which is quite cool. The code behind that is rather simple, so that's WebVR API. You get the VR devices, hopefully you get a bunch of devices. I just ignore that you might not get a device and just go for, yeah, just take the first one. Reset the sensor so that you always start with 0 no matter where the user is looking at the first moment. And then we start our render loop, and in the render loop, we use the orientation, we get the state from the device, which has an orientation and might have position data as well, and then you just reposition the camera to where the user is and make it look in the direction that the user looks at, and then you'll be good. That's what you need. This is the preferred solution to get your hands into it. Go ahead, have fun. The Oculus Rift works as well. It works also with the HTC Vive, and it works with OS VR. So that works pretty much the same way, and it's actually nice because this standard works with pretty much all hardware that comes out right now, and it's kind of standardized, which is nice. WebVR in 3JS is basically just another set of plugins. You have a VR effect that takes your renderer and renders in sort of like two different cameras in that. You have VR controls. VR controls just update, basically like the video texture. On each frame, you update it, and then you render the scene and the camera using the VR effect, and that's pretty much it. There's another thing if you want to play around with lower level or higher level stuff. There's a thing from Mozilla called A-Frame. A-Frame allows you to write looks a bit like X3DOM or X3DOM or VRML. You basically write a bit of HTML and you get these components, and this would basically create a scene with a cube on it, and then you can walk around the cube, which is a bit pointless but fun. Here's a few links. These are very important as we have just started to figure out how user experience works in WebVR or in VR. The Google Cardboard guidelines are a brilliant resource on what to do and what not to do, which is important because if you do it wrong, your users might vomit. And that's the thing that you definitely want to avoid. Right, to close up, Steve Jobs once said, amongst other things that he said that I find disputable, the computer is a bicycle for our minds. It's the most powerful tool that we've come up with as the humans. And I say virtual reality is a teleporter for our minds, which is even cooler, Steve. So, closing up, have fun, start exploring. It's not very expensive, and some events may actually give this stuff out. And slides are online. Thank you very much for listening. I'll be around for questions, and I hope you enjoyed it. And hopefully you start working with it. I think we have some time for questions left, I believe. Like 3 minutes or so. Any questions? Everyone's like, what the hell has just happened? What is this guy talking about? Yeah. Wonderful. In that case, enjoy the rest of the day and just find me for questions if you have anything. Yes, there's a question. Dun dun dun. Do we have we have a microphone.
Just a quick question. What about SVG, vector graphics?
It's cool. What is the real question here? SVG is brilliant. Aha, SVG technology for animations. SVG is wonderful. The problem is that browsers have recently just deprecated SMIL, which is a brilliant declarative way of creating animations in SVG. But you can still use CSS animations and JavaScript to animate SVG, which I hear is not perfect, but pretty good if you can. So that's the answer. For 3D, I would probably not use it, though. It has basically the same problems as does DOM and CSS, where it's declarative rather than sort of shifting or giving you control over what happens on the GPU. Any other questions? No one. All right. Thank you very much. I hope you enjoyed it and it was useful.